Hello, and welcome to today's webinar on design considerations that contribute to an efficient compressor system, brought to you by Plant Services and Kaeser Compressors. I'm Christine Lefebvre-Grace, Managing Editor of Plant Services. First, let me express our appreciation to you for joining us today. This webinar is sponsored by Kaeser Compressors, a global force in compressed air system solutions committed to maintaining the highest quality standards and delivering products that are built for a lifetime. Before I introduce our speakers today, there are a few housekeeping issues that I'd like to review. On your screen, you should have several primary sections. The upper left or audio control section allows you to adjust the volume of this presentation. Just hover over this section until you see the audio volume control and adjust the volume to your preference. To the right, in the largest section, is where today's presentation slides will be displayed. Under the slide window, you'll see a chat section where you can chat live with fellow audience members. At the left of the slide window is the questions and answers box, where you can type a question for the presenters at any time during today's webinar. We'll get to as many of those questions as we can during the Q&A session after the presentation. If we're not able to get to your question during the webinar, or if you have a question after the webinar has concluded, Neil, Wayne, and Kaeser will be able to answer these directly later, so ask away. The handout section at bottom left contains links to several resources, including today's full presentation and product information guides from Kaeser. Finally, at the bottom of your screen, you should see icons for additional features. By hovering over each icon, information about that icon will be displayed. If you're having technical problems, you can type in your question or concern in the question and answers box, and one of our technical engineers will assist you. If you need a better view, you can enlarge a section by clicking on the box in the top right corner of the section next to the X. If you accidentally close out of a section, you can get it back by clicking the Restore button at the bottom of the screen. It's located to the left of the icons. This webinar will be archived, and we encourage you to direct your coworkers to the recorded presentation. At the end of the presentation, we'll ask you to complete a very brief survey to give us the feedback that we need to improve our webinars. Now I'd like to welcome today Neil Mehltretter, Engineering Manager at Kaeser Compressors, and Wayne Perry, Senior Technical Director at Kaeser. Neil and Wayne are likely familiar to many, if not most of you, as top names in the field of compressed air management. So Neil and Wayne, thanks for being here today. And Neil, take it away.
Thanks, Christine, and thanks everybody for joining us. So let's start. Under normal conditions, the first thing we'd ask is, what compressed air equipment do you have? But is that really the first question that you should be asking yourself when you're talking about station design? When we break down compressed air, it's fairly simple, provided by an air compressor. However, that air has got to pass through piping, to air treatment, dryers, through storage receivers, and finally, to your points of use through distribution piping. And that doesn't necessarily cover everything. What if we simply said you need so many CFM at a particular pressure with a certain air quality level? When designing a compressed air station, these are the questions we'd recommend asking yourself or the equipment vendors that require compressed air in your facility. Just because you have existing compressed air equipment, they may not be the most efficient to meet your needs. Plus, the current location may not be the most hospitable. So let's examine these items a little further. How do you determine if you have the right mix of compressed air equipment? Typically, if the supply is meeting your demand and system pressure is always met, we tend not to worry about this particular detail. But do we have the right mix? So that's the question that we want to find out. One way to tell if you have a good or bad mix of compressed air equipment is to start in the compressor room. So, that's the fundamental thing. Looking at equipment on paper, everything may be fine, but what you necessarily can't see on paper is whether you have access to the compressors. Is it a hot, dirty, dusty environment in the compressor room? What's the duty cycle your compressors actually have? You'll also see that we listed air quality among the items that you want to review during a walkthrough. When you're walking through the compressor room, check if there's water in the receiver tanks. Are the electrical demand drains actually working? Where's the condensate actually running to? These are some of the quick points you'll be able to see in the compressor room that may be missed, or most likely will be missed, just by reviewing a piece of paper. If you check out the picture on the right, you're going to see two compressors. Those units are identical. The compressor on the right was operating without issue, but the compressor on the left continuously overheated. when reviewing data from the 2 units, operating temperature of the unit on the left was elevated, but that data couldn't explain why. The picture really says 1,000 words here. The left-hand side of the compressor was ingesting hot air, recirculated air from either itself or the unit on the right, as the cooling air discharge wasn't directed away from the units. The temporary ducting that you see on the machine was here to help prove a point to show that with ducting, the units could operate properly. And also, in that case, is actually reducing the overall operating temperatures and those nuisance shutdowns for the unit. So what we found is this provided improved reliability and longevity of the compressor. Speaking more specifically about accessibility, let's face it, if your compressed air station is working well, there's probably little to no reason for you to go in the compressor room. But over time, this manifests as your compressor room is becoming additional storage spaces like you see in the pictures at right. Keep in mind that in order to properly service your air compressor, you need so much room on any given side, and therefore using your compressor room for storage is not recommended, certainly not the way you see here. Also, the NEC code requires so many feet in front of an electrical control cabinet, as well as other state and local laws that you might have to adhere to. So, in general, keep your compressor room clean and safe. Many plants are going to grow over time, and this is a good thing for both end users and also compressor manufacturers. So what worked in the beginning may not be appropriate for the future. So here are a few examples of plants along with their compressor rooms that you see on the right. It's a bit hard to read, but I think you get the idea that they can vary significantly. Specifically, the age of facilities can also affect piping runs and compressor locations. Not only should the compressor room be big enough to house all of your compressed air equipment safely and with sufficient service access, like we just talked about, but you should also consider where in the facility those compressors are located. Normally, your compressed air system is going to be installed near other major utilities such as power, water, and gas. Keep in mind that your compressor has a significant amount of recoverable heat, either through space heating or water heating, and therefore, if you have a process in your facility that could benefit, it may be advantageous to locate your compressor room near that process. Plant piping runs should also be considered when placing your compressors in the plant, as well as centralized or decentralized compressor rooms. Pipe size, length, and type, such as branch or loop, will also affect overall capital cost, but it will in the end affect production via operating costs and possibly air quality, which we'll talk a little bit about later. So this is one of my favorite slides, and what goes in has got to come out somewhere. So in addition to where the compressors are installed in the plant, you have to consider where the intake air is actually coming from. Compressors ingest ambient air, and this air is going to come out into your plant processes. If your compressor room is located near exhaust fumes, like the picture at the right, or other contaminants, possibly like what we see in the picture at the left, those contaminants have an opportunity to be passed on to the end use. Certainly, filtration can be installed to remove hydrocarbons. However, this is an item that must be considered during your design phase. Note that if your facility is near a pasture, you may not have a choice in how the wind blows or the quality of the air ingested by your equipment, so you want to take this in mind during your design phase. In some cases, like we're seeing at the facility at the right, you may not have room within your plant for your compressed air equipment. So, note here is that installing industrial equipment outdoors isn't recommended. However, there are options, such as package systems with full enclosures that could be offered to protect your equipment from the elements. As you can see from these pictures, care must be taken in not only where you place the equipment, but how the equipment is conditioned to operate. If low ambient temperatures are expected, and this can even happen indoors, care must be taken to ensure that water cannot condense within the compressor when it's offline. As mentioned in the previous slide, we don't recommend outdoor installations, but the pictures shown give you an idea of how exposed compressed air equipment really can be, even inside. The harsher the conditions, the shorter mean time to failure, and the less reliable the equipment will ultimately be. To sum up the points we've discussed regarding ambient conditions, strive for installations which are located indoors in clean, temperature-controlled environments. It's crucial to have easy access to the equipment. The location of the compressor room is also important, as is what other equipment might be placed in that room. Finally, one thing that we haven't really mentioned is to consider VFDs and maybe the vulnerability of a VFD prior to installation as to whether or not your designated install location is going to be hospitable for those kind of drives. Excuse me. Well, now that we've discussed where to install your compressor room, let's talk more about the ventilation within that compressor room. Ventilation should always be paramount consideration for each compressor and dryer. As mentioned, your compressor is a very efficient heater. In newer compressors, you're looking at upwards of 96% of electrical energy that can be converted back into a heat recovery mode. So if you're not using that heat, it's got to go somewhere. Since your compressors are giving off a lot of heat, it's going to need to be ventilated. Don't forget that your dryers may give off some substantial heat as well, and that should be removed via a fan. Like we discussed, ambient condition of your room, both on the low and the high end, can affect operation of this equipment. If the room's too cold, compressor oil may be too viscous, and possibly if there's any standing water in your equipment, that could freeze. Therefore, all compressor manufacturers give a minimum operating temperature threshold. This is usually above the freezing point of water. Likewise, coolers, motors, etc., those are going to be sized for specific temperature ranges. Operating above a certain temperature can shorten the lifetime of your equipment as well, basically reducing your reliability. We already discussed inlet air, but remember, it's got to come from somewhere. Typically, this is going to be outside the compressor room, as you can see in the picture on the right there. In this case, inlet air is going to come via a louver damper. These louver dampers also serve to bring in the cooling air that you need to keep an air-cooled machine within temperature. Air from outside also ensures this can provide proper cooling. However, in wintertime, you may need some recirculation of the compressor hot discharge air to mix with that outside ambient air if it's too cold outside. And you can see a recirculating duct just above that yellow compressor there, right in the middle. Most sites have temperature controls to ensure the room stays between 60 degrees and 80 degrees Fahrenheit via a combination of temperature sensors and actuators to open and close inlet louvers and dampers, as well as recirculating ducts on your compressors. And this is a good practice. I like this graphic because it puts it all together: compressors, dryers, condensate, receivers, but it also shows the ducting. This gives you a great general overview of airflow within a compressor station. Notice that both compressors and dryers are going to require fresh air, and they're also going to give off hot air. Best practices consider inlet air, cooling air from one side of a room, and then the discharge hot air to another or multiple sides. This avoids unplanned recirculation, which we're going to see later on multiple times. Unplanned circulation can cause overheating and shorten the lifetime of your equipment, as well as negatively impact reliability and uptime, which we've already discussed. Duct size, run, and whether recirculation is included are all items to consider within that compressor room. So we've already established that air-cooled compressors need cool ambient air in order to operate efficiently. The compressor is going to need cool air for that summer operation, and you want that air to be as clean as possible. Using a thermostatically controlled inlet louver damper like in the picture at right, that's going to allow you to regulate how much of this air enters the compressor room. When coupled with recirculation, this is going to provide a degree of control over the temperature in the compressor room, helping you keep it cool in the summer months and warm in the winter. However, one thing, installing a louver damper in an opening is going to reduce the free area of that opening. And this is true not only for thermostatically controlled units, but really any louver, damper, or bird screen. And keep in mind, even water-cooled compressors need fresh air. So let's talk a little bit more about those. Here we see a general compressor room from the outside. So free area is what we want to focus on here. Free area is actually the area of, excuse me, unrestricted area of an opening. But You want to take this into account when sizing openings in a wall. Begin by determining what the free area rating is for the device you're installing, so louver, damper, bird screen, etc. Then you have to oversize your opening so that that total free area requirement of the compressor is still met. So let me give you an example. If you need 30 square feet of free area for your compressor, and you're planning to install a thermostatically controlled inlet louver in that room, you already know that that opening in the wall has to be larger than 30 feet, but how much? So let's assume you're using a louver that has a free area of 50%. This means that every square foot of that louver, the free area is 0.5 square foot and the blocked area is 0.5 square foot. So if you need a total of 30 square foot of free area, in our example, you need to double that. So that ends up being 60 square foot. The picture shown here includes inlet louvers in the bottom and discharge ducts at the top. So that's what you see on the right-hand side. You can also see a roll-up door to the left. When roll-up doors are open, like you see here, or partially open, typically there's really not enough fresh air to reliably run your compressed air station. But when it's closed, you may experience overheating. So if you have these symptoms or you notice that in your own facility, likely you don't have enough cooling air inlet, and it just simply needs to be bigger. Ducting is absolutely critical to having a well-operating, long-lasting system. Compressors generally have a location for cooling air discharge, and this is where the air leaves the compressor package, and this is the same for dryers as well. Without ducting, that air is going to enter the compressor room. Disregard the physical size of that exhaust location and size your duct based on the compressor's cooling airflow, the maximum permissible pressure drop, and any other pertinent information from your compressor manufacturer. The size of the opening is independent of how big the duct needs to be. In most cases, the exhaust duct will need to have a larger cross-section than this opening. Maximum permissible pressure drop is key. Compressors generally have an internal cooling fan that pulls cooling air into the package and then forces it out again. This fan is, in effect, both pulling and pushing air. When you connect ducting to either side of this fan, it creates a pressure loss. This applies to the area upstream of the fan, which is inlet ducting, and downstream of the fan, which would be exhaust ducting. For a given flow rate, the smaller the cross-section of the duct, the larger the pressure loss. The more complex the path of the ducting, bends, elbows, adapters, etc. As you can see in this picture, you've got basically a cone, if you would, that's going to a smaller space and then running out. So what that does is it restricts the flow, causes the machines to overheat. So let's talk a little bit about more complex ducting designs. The picture on the left just shows your compressor room. So if you just looked at the compressor, you say, okay, well, maybe that's not too bad. The picture on the right shows the ducting from the compressor to the roof. So you can see that there's quite a few bends. The run itself is quite long. So as noted on that previous slide, internal fans only have so much pressure drop that they can handle. And when duct runs include too many bends and have long runs, that pressure drop is going to add up quickly, and that equates to overheating compressors. So longer straight runs, they're going to make a difference, as well as making the duct dimension as wide as necessary. The smaller the square footage, the higher the pressure drop, and the less reliable your system is going to be. When multiple ducts come together, how can you ensure that that hot air is going to be removed? Well, a booster fan, which you can kind of see there at the top right, that's going to help remove the necessary heat, but it's got to be sized appropriately, and you need to always consider what happens to the equipment should the booster fan fail. If it fails and all the equipment's running, likely you're not going to be able to remove all the heat you need to, which again will result in equipment overheating and shutting down. Not only lost production for you in the plant, but also reduce mean time to failure, and then the lifetime of your equipment is going to be lower. This is a similar scenario as that previous slide. We've got multiple ducts from compressors in this case. They're feeding a main header with the booster fan. So the booster fan you can see small on the right-hand side before it ends the picture. However, the point to highlight here is What happens if, let's say, 2 of the compressors are offline, not running whatsoever, and only 1 compressor is running? If there isn't a backflow damper on each of these compressors, there's the possibility of hot air from that 1 compressor that's on to feed the offline units, thereby increasing the likelihood of overheating for them. So booster fans will certainly help, but it shouldn't be the only protection that you're considering. It may not look like there's a lot going on with this particular picture, on the one on the left and the one on the right. It's the same duct, if you would, but let me break it down for you a little bit. First, the duct was sized exactly to the cooling air discharge of the machine, so that's what we said was kind of a no-no, if you would. As mentioned, the size of the cooling air discharge is not indicative of the necessary duct size, so it has to do with pressure drop. And often it's very far from reality. This particular duct was marginal at best, and so we had some back pressure issues and some overheating issues. Consider the size of the cooler as a baseline point for how big the duct needs to be. Certainly a starter, but not an end-all be-all. The length that you're ducting to the ceiling or outside also needs to be considered in that overall pressure drop calculation. In addition, bird screens not only on the inlet but also at the discharge need to be considered. So inlet to the room and then discharge like you see there with the duct outside. Otherwise, you may have some unwanted guest in your compressor or your compressor room. Plus, if you don't have a gravity dampener on the outside of your facility, warm or cold air can easily get back into your compressor, which can keep it from staying loaded or starting. Other ventilation influences are other equipment in the room. So we saw that with our original example with those 2 compressors side by side. Cooling air discharge from one piece of equipment can easily be ingested by another. Further, if there are other gases within the compressor room, those could potentially be ingested to your compressors and dryers. Lastly, if your facility is a full washdown facility, be sure to consider where you put your compressors or what type of protection you have for these units. Note that most machines are only an NEMA 12 enclosure and are not rated for a full washdown. So lastly, we'll talk a little bit more about recirculation, show another image, so maybe that might help solidify this. But let's take a specific look at it as a means of temperature regulation that's energy efficient. In comparison with HVAC or space heating applications, it's much more energy efficient because it uses the heat from the compressor that's already been made, if you would, and requires less electrical input. These systems vary in complexity, but at its simplest, the concept is going to work like a railroad switch. So you're moving exhaust air either down track A out of the room during high temperature periods or down track B back into the room during those low temperature periods. Recirculation involves a thermostatically controlled damper in the ducting train of the compressor, and that links to the thermostatically controlled inlet louver that we've discussed previously. So as temperatures increase in the room, the inlet louver is going to open, allowing cool air from the outside into the room, and the recirculation louver is going to close, forcing that warm air exhaust out of the room via the ducting train. As temperatures decrease in the room, that inverse happens. The louver is going to close, preventing cool air from outside from the plant entering the room, and then the recirculation louver is going to open, forcing warm exhaust air back into the room in order to raise that temperature. And this is going to continue until the desired temperature is achieved and there's a balance, until, of course, another adjustment is required. The best ways to avoid inadvertent recirculation is to ensure that it works properly. But there are going to be times when compressed air equipment is accidentally recirculated into your cooling air. And this typically is when cooling airflow pattern is poorly thought out or when systems evolve over time and equipment is added bit by bit over the course of many years. We've established that compressed air equipment generally draws cooling air from its immediate surroundings. This can be a problem if some equipment exhausts toward the inlet of others, which we saw before. This is referred to as that unplanned recirculation. And it's where the cooling airflow for one machine accidentally ingested by another. So again, This picture just shows that inlet is directly near the discharge ducting, and so what you end up having is a cooling loop that you don't really want to have, so your warm air is going back into your inlet. So how to avoid it? So the best way to avoid it is to use ducting and employ the points that we made earlier: thermostatic control, inlet, and recirculation louvers, and then also to prevent or to have prevailing direction of cooling airflows whenever possible. So cooling airflow from one side, hot air discharge to another. Having the majority of your airflow in one direction, that helps prevent accidental recirculation. Try to route exhaust air through the roof when possible, and take those prevailing winds and other site conditions into account. It's typically not a problem to exhaust through one wall either, but as long as the cooling air inlet isn't being pulled into the room on that same wall. If you have to do that, like we saw in the previous slide, then orient the exhaust so it's pointing away from the inlet. So what we see on the far right is you've got some hoods that are blowing the hot air up, which allows the cooling air at the bottom to avoid entraining that hot air. Now that we spent some time within the compressor room observing some key points, let's talk about what equipment we've actually got in there and whether it's the right stuff or not. How do you determine that? An air audit measuring flow, pressure, power, and compressor operation is going to help you determine how much air you're using now and whether it's operating efficiently and effectively. So now that you've got a handle on what you're using through an air audit, you can go about figuring out what's the most efficient operation and whether you have the right constellation of equipment. Systems will run most efficiently with base load and trim load compressors. Just like it sounds, base load units should always be on and loaded, while trim loads are going to come on during peak demands. VFD compressors could be considered peak load or trim load compressors as well, but depending on your demands, you may just have one VFD or even multiple VFDs operating the facility. In addition to compressor selection, dryers and filter selection will ensure you have the appropriate air quality level at all times. Compressed air dryers should be sized for worst case conditions as well as air quality required and system operating pressure. Likewise, the type of dryer is going to make a difference, whether you need a refrigerated dryer, so say a 38-degree Fahrenheit pressure dew point, or a desiccant dryer, which is a minus 40-degree pressure dew point, or really anything below 38. So you need to determine that. Over-treating the compressed air can significantly increase your lifetime costs and should necessarily be avoided. Lastly, piping storage and master controllers are going to make a big difference on how efficiently your station operates. I like this slide because it kind of breaks down most of what we've already talked about. Compressors, installation location, dryers, and filters. We haven't quite gotten to storage yet, but compressor rooms are made up of the items that we noted above. And I'd say these are probably your major components. But we typically add on secondary items, and hopefully these items are addressed during your design phase. But we spend a lot of time talking about ventilation, and we're going to talk a little bit about storage as well as piping here. System piping can make a huge impact on overall compressed air operation. We don't have enough time today to cover everything to consider, but the highlights would be, don't settle. Put in pipe that won't corrode over time. Size for future growth. Make sure your drops come from the top to ensure that water doesn't get entrained to other points within that system. And finally, loop your pipe where possible to reduce pressure drop. Excuse me. Here's a quick example regarding pipe sizing. If you had a 100 psi compressed air system and 1,000 feet of pipe with about 1,000 CFM, so in this example, if we had a 2-inch pipe, we'd have about 77 psi worth of pressure drop after that 100 foot of pipe, so only about 23 psi at the other end. That's an extreme example, but if we simply doubled the pipe size to 4-inch, that pressure drop is now only about 2.2 psi, so obviously a lot more usable pressure to the point of use. You may not have 1,000 CFM today, but 5 years from now, that could be possible. So future sizing is a good thing. Now let's discuss some system storage. We can break down storage into 3 types: wet, dry, and point of use. So here we see a nice graphic shows the location of various receivers. Note that wet and dry receivers are typically in or near the compressor room. And this example also shows loop piping networks within that main air system, so in those 3 different segments of the building. Also a good practice. For storage, it's important to understand the different types of tanks. Wet tanks for knocking out initial volume of moisture, those are going to be located upstream of air treatments or dryers and filters. Not just for storage, but really for individual compressor control. That's when we typically see it. Dry receivers, I would say specifically for storage, located downstream of air treatment, so it's storing dry air for those points of use. Ideally, most systems or ideal systems would have both tanks, but not always practical due to space. Point of use receivers, those are great for high intermittent demand events, and you should also consider meter storage for those applications. An air audit's a great way to figure out the design for these size tanks. You may not have enough storage in your system if you notice your compressors are rapid cycling, or they have higher energy costs than expected, as well if system pressure drops during intermittent high demand events. Keep in mind that this is something worth fixing as dual control or load on load units without proper storage will consume up to 10% more energy, and that's a minimum number. And you also have to consider the reliability of those units and the service costs without proper storage. There are formulas for calculating the right amount of storage needed for every system or every application, but if you want a general idea, if your receiver is large enough, wet tanks should be, as a rule of thumb, 1 to 3 gallons per CFM of your largest cycling compressor. Dry tanks should be 3 to 5 gallons per CFM of your largest cycling compressor. You want to also check the location and connection for the receivers. Even if the receiver is large enough, if it's not close enough or properly tied into the air main, you may have problems. In summary, before I hand it over to Wayne, be sure that you're aware of your equipment's comfort zone per manufacturer specifications. Compressors are going to put off a lot of heat, and if the airflow in the room isn't adequate, they won't work properly. Make sure your inlet and discharge openings are appropriately sized. Take full advantage of the heat generated by the compressors and consider recirculation of hot air when useful, but avoid inadvertent recirculation. It's not just your compressor that needs ventilation. Your dryer should also be taken into consideration, as well as anything else in your compressor room. And remember, it's not just your compressors. Piping, storage, dryers, filters, and master controllers, they're going to make a big difference on your system efficiency and reliability. So thanks for your time, and Wayne, off to you.
Thanks, Neil. I'm going to talk today about how system design affects the reliability of the components in the system, how it affects your capital spend, how it affects your production equipment, and as you can see in the picture on the right, how it affects safety. And I would like to say that this is not the first time I've seen a compressor installed in a restroom, but it's the first time I've seen the condensate drain plumbed into the toilet lid. and that is a safety issue because the condensate comes out at 100 psi, and if the lid is up, it's going to shoot it straight out. I do want to talk today about a system that is typical, and we have measured these systems. And it's a problem with single compressor systems and multiple compressor systems that don't have a master controller. In this particular system, it was a compressor, filter, a dryer, filter after the dryer, and a tank. And all of these components were areas that all of these bar graphs show areas that we were measuring. The lower part shows you what the actual point of use pressure was. And when we started measuring, it was down, and the control range of the compressor was from 100 to 110 psi, but the point of use was only getting 70 psi. This gray area is what we call the dirty 30. That's the connection from the header down to the point of use. And in this particular plant, they had 15 psi pressure drop because they were using just these 1/4-inch hoses going down to the point of use and not a full-size hose. The blue area here represents the pressure drop through the main header, or what we call droop. And that is, we measured the pressure where the compressors were putting air into the header, then we measured the pressure in the header at the farthest point, and we had about a 5-pound drop in that. The red area is the pressure drop through the air treatment equipment, the dryers and the filters. And in this system, we measured about 10 pounds of drop through those systems. At the very top, that's the pressure that the compressor was seeing to control over. So in this case, it's sitting at 100 psi. That's its load point. It unloads when the pressure gets up to 110 psi. Pressure drop is caused by resistance to flow. When the flow stops, the pressure drop goes away. And in this case, we can see that as soon as the compressor unloaded, the pressure drop through the air treatment equipment went away, and the pressure dropped 10 pounds. In this case, was only a 1 pound change in the pressure at the point of use was causing a 10-pound fluctuation at the compressor pressure transducer. Go back a slide. What happens in situations like this is the compressors will load and unload in rapid cycle, just like Neil was talking about rapid cycling. We have instances where we have measured literally millions of cycles in a 6-month period on a compressor, when the cycle time should have been in the hundreds or the thousands. Now, if you think about that, that million cycles cycled valves, cycled solenoids, cycled diaphragms, millions of times. That's going to result in their failure prematurely, basically. You're not going to get the life out of the equipment if this stuff is cycling like that. So it's very important to put a system together so that you don't get this kind of cycle time. In this particular case, one way to eliminate that is start working on, do I have the filters sized right in the air treatment train? Do I have the dryer sized right in the air treatment train? Because you shouldn't have 10 pounds of pressure drop across that. Should be more like about 3 or 4 pounds of pressure drop. The other thing that could have helped in this situation was putting in a wet tank so that you have a little bit of storage between the compressor and the air treatment equipment. That gives you a little bit of a buffer and allows the machine to have a little longer total cycle time. Now, how does it, another way system design affects reliability is, as Neil talked about, how hot does the thing get? We've seen it, the compressor installed in the toilet. Now we have 2 compressors installed in a closet. These are 15 horsepower compressors. So that's about as much heat as a 20 kilowatt heater put in that particular closet. If you look up at the top, this is in that same closet. You can see that they did put in a vent fan in the roof up there and the ceiling up there, but that's certainly not sufficient to get all of the heat out. If you look closely, you can also see that the piping is hard piped to the heat exchanger on the built-in dryer in this case, and the pipes are not supported. What happens here is any vibration in the pipe or the compressor is transferred straight to the heat exchanger in that dryer, and you're going to have a premature failure of that heat exchanger in the dryer. So always be sure that you have a flexible connection in that piping and that you have the pipe supported so the weight won't damage any of the components. This is another example, hard pipe right out of the discharge of the compressor, unsupported pipe, and this pipe is connected directly to the aftercooler on the compressor. So any vibration that goes in there and the weight of that pipe is all hanging on that aftercooler, and you're going to eventually lose the aftercooler. One other thing that we see is, as installed, pipe hangers might be holding the pipe properly, but as soon as the system turns on and there's air going through the system, these pipes will torque. So you need to go back when the system is on and recheck all of the hangers to make sure that the hangers are actually supporting the weight of the pipe. In this case, as the pipe lifted off the hangers, all of that weight gets transferred back to the compressor itself. Now, overheating is a significant issue with rotary screw compressors, or can be. And in this case, the customer did a wise thing by buying a remote mounted intake filter, but he mounted the intake filter right under the exhaust duct for the compressor and was recirculating the heat. You have to remember that the compressor lubricants are all based, the time that they can run is based on 180 degrees Fahrenheit. So if you buy an 8,000 hour compressor lubricant, that's based on running 8,000 hours at 180 degrees F. Every 18 degrees over that you run the compressor, you reduce the lubricant life by about half. So an 8,000 hour lubricant becomes a 4,000 hour lubricant. In this case, the customer was losing his lubricant, losing his lubricant in a matter of months, and eventually was losing air ends, simply because he didn't put the intake filter far enough away from the exhaust duct. Now, we also want to talk about how poor design can affect your capital spend, and this example is a good one. Because he was running at elevated temperatures, the aftercooler couldn't get the discharge temperature of the air down to 100 degrees F, and 100 degrees F is where he was the design point used to purchase the dryer. So he went, and all he needed was a refrigerated dryer, but because he had water in the line, because he was overloading the dryer with hot air, he wound up buying a desiccant dryer that he didn't need and wouldn't have needed had he just kept the compressor cooler by changing the ventilation. Another thing that affects capital spend is using the wrong pipe size. Again, Neil touched on that subject, and here's a nice example of going from about a 3-inch pipe down to a 1.5-inch pipe to go into the distribution system. What happens in cases like this is you wind up with low pressure in various parts of the plant, and a lot of times the solution to having low pressure in a distant part of the plant is to buy another compressor and locate it near the area of low pressure, when in fact, compressor was not what you needed. What you needed to do was correctly size the pipe. I've been in plants that literally had over 300 compressors in it, and 200 of them are over 100 horsepower, simply because they couldn't get air through the pipes that they had, and they were dropping compressors all around the plant. If they had correctly sized the pipe, they could have saved about $600,000 in capital and almost $300,000 in maintenance expense on that $600,000 capital spend for compressors. So it's really important to do the right design in the beginning so that you don't spend capital you don't need. Another thing that happens with poorly designed systems is that you wind up hurting your production equipment. In this particular case, you see the water draining on the floor. We went into that plant, opened the drain valve on the dry receiver, on the receiver that was downstream of all of the air treatment in the plant. We drained about 200 gallons of water out of the dry receiver. That plant had been having problems with cylinder failures, solenoid failures, and all kinds of equipment failures because they were getting water downstream in their system and draining water out all throughout the plant. All of this was because they had improperly sized the drying equipment and the cleanup equipment and didn't take care to keep an automatic drain on their dry tank so that they would know that they're getting water in the dry tank. And really, that's going to end it for us. And Christine, we're going to turn it back over to you now.
Well, excellent, Wayne and Neil. Thank you so much. You've, again, covered a lot of important ground here. So much of it comes back to just paying attention, just minding those details, putting some forethought into making sure your system is actually designed for success. That whole, spend some time up front and prevent major headaches later. We'll go ahead and we'll turn now to the Q&A portion of our webinar. Looks like I have a question to begin here. All right, either of you can take this one. How can I tell if my compressors are fighting each other?
Yeah, that's a great question. Normally speaking, when the person that's driving the fork truck around the plant comes and tells you, hey, something's wrong in the compressor room, you know someone's heard something or seen something. Usually what ends up happening is you hear a and then one machine's loading and one machine's turning off and vice versa. So you can hear it. You can also see it in the operating pressure of your system, where pressure is low, then it goes up. You can also see it in that rapid cycling that we talked about as well. So, typically if you have more than one compressor and those machines are loaded, you want to take a look at what that pressure drop is in your air station. So if you're trying to avoid it, let's say, so if you turn one compressor off and widen your pressure band, let's say, you can figure out if only one compressor is needed to operate that system. So, that's one thing I would definitely look at. You can hear it. Sometimes you can also see it if you're looking at data. So we didn't really talk about this in this webinar, but if you're looking at, let's say, a key performance index of compressed air, which would be specific power, anything under 20, 22 kilowatt per 100 CFM, I would say would necessarily be a fairly decent specific power, depending on what operating pressure you have. But in cases where compressors are cycling quite a bit, you're going to be over that 20, 22 kilowatt per 100 CFM threshold.
Neil, I'd like to add one more thing in there. If you don't have an air assessment done, you don't have the system instrumented up, one of the things that I always do is take a single pressure gauge and check the pressures, the control pressures at each compressor that's in there to see if they're fighting each other, because oftentimes the compressor gauge itself or display is going to be off by a few pounds. And you might think it's going from 100 to 110, when in fact it's going from 97 to 107. Right. So take a single gauge and check the pressure at both compressors off of this single gauge. Then you can tell whether the gauges match on the compressors. You can often find that they're fighting each other simply because you thought you had them set right and they're not.
Yeah, that's a great point. All right. Next question. What would you say are the most important design considerations within a compressor room?
Ooh, yeah, that's a loaded question. Thanks for providing it. If you ask me any day of the week, I might come up with a different answer. And
Sure.
I think that's a hard question to answer. To it really depends on what I think the most important thing for you is. I spent a lot of time talking about ventilation here. And so, for me, what you have in the room is going to make a huge difference in getting that heat out. So, for me, if I'm just considering, I've already planned what the compressors are going to be, I already know what the demands are, ventilation for me would be paramount, but I think Wayne probably has a different perspective on it.
Well, we've taught for years and years to look at the compressed air system as a total system and not as just a group of components. But if I'm designing, if this is a greenfield plant, I would take the whole plant as a system. As to what Neil talked about heat recovery before, look and see if you have the opportunity for heat recovery. Locate the compressor station near that opportunity. If it's a food plant, you always do clean in place. You're using hot water. Use water cooled machines. A 100 horsepower compressor is basically a 75 kilowatt heater. You might as well use that heat. It's a BTU to BTU offset for whatever you're using to heat the water. But that would be the first thing. Then ventilation and distribution piping. Those are the two big areas that I see that are neglected, or they're given the short thought when it comes to putting the system together. They'll buy the compressors, the dryers, the filters, and then neglect to use the right size pipe to get the air to where they need it. I think that's really important in the system design.
Well, and it seems like it's so easy to think too that, okay, I'm not in a greenfield situation. I don't have the luxury of starting from scratch, but it doesn't mean that you can't make meaningful improvements and go back and take another look and put some foresight into how
Christine, you can't
make things better.
Yeah, you can't eat an elephant in one bite. So if you've got an existing system, take a nibble here and a nibble there, get with your service provider, find out what the optimum system should look like. Right. Then start just biting off little chunks of that and making sure you have a plan, an implementation plan, so that over the next 5 years or so, you can get that system more optimized.
Right, but just start somewhere.
A lot of people look at it and they think, this is overwhelming, this is too big, we can't. But if you bite it a little bit at a time, you got a chance to get there.
Exactly. All right.
Normally it didn't go bad overnight, so you're not going to fix it overnight.
That's an excellent point. That's the quote of the day there. All right. Our next question: are service intervals really necessary? Can I just have someone visit twice a year?
I couldn't understand.
Are service intervals really necessary? Can I just have somebody come twice a year? Question.
If you only run the compressor for a few hours a day, you might be able to get somebody to come twice.
Right.
But yes, the service intervals are critical. The lubricants, whether it's a dry running screw or whether it's a lubricated screw, whether it's a centrifugal machine or a piston machine, manufacturers have given you service intervals to say, if you service the machine at these intervals, you're less likely to have a failure than if you don't. It's the unintended failures that cause the whole plant to go down. So I would go by the service intervals and schedule maintenance around that. The other thing that you have to remember in a poorly designed system, you're doing service intervals based on running hours, not necessarily loaded hours. You really want to make that system where the compressors run loaded or they're off. That way you only do the service. You're maximizing your service dollar by doing the service on machines that have actually loaded time and not a lot of unloaded time. And we do see machines that might have 300 hours of loaded time and 2,000 hours of unloaded time. They still got to do a 2,000-hour service, but they only got 300 hours of load out of it. That's another thing to look at system design to reduce your maintenance costs.
Yeah. All right. Well, it looks like we've got time for one more question here to wrap up. How can I tell if my compressor is oversized?
Well, Wayne just gave a good example with the 300 loaded hours and 200 service hours. You know, that if you're just going to look at two numbers on your compressor, those are probably the two numbers that I would look at, and that's going to determine what your duty cycle is. So it doesn't mean that just because you have such a, let's say, a low duty cycle, that you don't need that much air. But it does mean that you don't need that much air all the time. So that's going to be very indicative of being oversized. And what that ends up doing is, you know, it's increasing your overall energy consumption and you're running that machine at a very low duty cycle, which means that you're probably efficiently making a lot of water, which will fail the air end pretty quickly. So those are things that you'd probably want to consider figuring out if you're oversized.
If you don't have, if your control on your compressor doesn't have a register for loaded hours and unloaded hours, you can simply take a stopwatch or a smartphone and time the load cycle and unload cycle. And if it's loaded for 30 seconds and it runs unloaded for 2 or 3 minutes, and then it loads for 30 seconds and it unloads for 2 or 3 minutes, that's indicative that the thing is oversized. If you have a modulating compressor where you don't have those load-unload cycles, on most modulating compressors, you can adjust their variable differential pilot valve, turn them into load-unload just to time those cycles and see where it's at, where you're sitting. And that's an easy way to determine whether or not you've got an oversized compressor.
Okay, that's excellent. All right. Well, Wayne and Neil, I'd like to thank you again so much for your time and your insights today. We'd like to thank also our sponsor, Kaeser Compressors, and to all of you who joined us today. We want to remind you this webinar has been recorded and it will be available shortly for on-demand viewing. You're also encouraged to visit plantservices.com to gain access to even more tools and resources aimed at helping you achieve success. Today's full presentation also will remain available for on-demand viewing in the handouts area. Did you like this presentation? Let us know your thoughts by answering our brief survey that will appear on your screen shortly. Your candid answers are not only appreciated, but also they help us craft future events. Thank you so much for your attendance today and have a great rest of your day.